Module 1, Lesson 4, Construct a Perpendicular Bisector. We're starting this lesson with some vocabulary that is familiar to us. We have equidistant, and a point is equidistant from two different points if it is the same distance from both points. We know this equidistance equal length, which means it is going to be congruent. We are going to have congruent segments. Next is a definition of a right angle. We know that a right angle is an angle with a measure that is exactly 90 degrees. This is going to be a useful definition for us when we do proofs. Definition of perpendicular. This follows the right angle, and we use this symbol for perpendicular. If two lines intersect to form a right angle, they are perpendicular. The definition of perpendicular is right angle. Two segments or rays are perpendicular if the lines containing them are perpendicular. So if we look at our diagram here, we can see that segment AB is perpendicular to line CD. We can also say line CD is perpendicular to line AB. And notice here, how do we know these are perpendicular? One, we are told they are perpendicular, or on our diagram, we have a right angle mark, because perpendicular means right angle. So if we are told they are perpendicular, we can mark a right angle. If we have a right angle mark, we can say they are perpendicular. Now, while we're looking at this, I want you to see something else. This is a straight line. These are a linear pair, and we know that a right angle measures 90 degrees. So we know that this angle measures 90 degrees as well. The linear pair postulate says they are supplementary, and 90 plus 90 is 180. If we also look vertically, we are going to have the same angle pairs here. So this would be another right angle, and this would be another right angle. When you have two lines that intersect, if one of them is a right angle, then all of them are right angles. If your two lines are perpendicular, all of them are perpendicular. So this is very useful. This follows with definition of perpendicular bisector. This is really two ideas for the price of one. The first thing that's happening here is we have perpendicular. What does that mean? That means they're intersecting at a right angle. And idea two is bisector. Do you remember what bisect means? Bisect means we have two congruent parts. So in this case, we have a line segment or ray that is perpendicular to a segment at its midpoint. And do you remember definition of midpoint? That's where we get our two congruent segments from. So if we look at our diagram over here, we have segment CD is the perpendicular bisector of segment AB. Now, order matters when you write something like this. How do we know that CD is acting on AB? Well, look here. We can see we have a right angle marking that tells us that it's perpendicular, and we have congruent marks on our segment. That tells us that AB is being cut by CD. So we can also say that point D is the midpoint of segment AB. And how do we know that? Because segment CD is the perpendicular bisector. Definition of perpendicular bisector is it is perpendicular at the midpoint. So we can say point D is the midpoint. Midpoint, bisect, congruent, all of those go together. You have one, you have all. So we can say a perpendicular bisector bisects a segment into two congruent segments. If we know CD is the perpendicular bisector of AB, we know that segment AD is congruent to segment BD, and by definition of congruence, length AD equals length BD. So a lot of really good definitions in this section. The major concepts that we are going to be talking about, these are some big ideas here. An angle bisector, which we did last section, is related to a perpendicular bisector. Now, if 2 points are symmetric, what does symmetric mean? Symmetric just means a reflection. There is symmetry. With respect to a line, if and only if the line is the perpendicular bisector of the segment that joins the 2 points. The next idea here is any point that is on the perpendicular bisector is equidistant from the endpoints of the segment. Now there's a lot of words here. We're going to look here and break this down and see what this is all about. So in our diagram, we consider segment EG. So let's mark segment EG. There's our endpoints, there's our segment. When the angle is folded along line AJ, or ray AJ, so AJ comes up the middle here, we're going to fold our angle along that line. Point E coincides with point G, so think about folding this over. Now, what do we know about ray AJ? Take a look down here. What do you see? AJ is the angle bisector. We have 2 congruent angles here. This is the bisector of this angle. So it makes sense that if we fold it in half along the bisector, we get half our angle. Well, if E folds down onto G, this demonstrates that point F, right here, is the same distance from point E and point G. So our length EF is the same as our length GF, which means that those 2 pieces are congruent. If those 2 pieces are congruent, F is the midpoint of the segment, and it is also on the angle bisector. A big idea here is that the angles formed by our segment EG and our angle bisector ray AJ are going to be right angles. So we have congruent segments because of our midpoint F and a ray that is perpendicular to that segment that passes through our midpoint. Are you seeing perpendicular bisector here? Let's look at our next 2 ideas here. 2 points are symmetric with respect to a line if the line is the perpendicular bisector of the segment. So this is kind of the opposite of what we just did. And a perpendicular bisector of a segment passes through the midpoint and is perpendicular to the segment. Now, what all of these words lead us to, and these ideas lead us to, is our next 2 theorems. And remember, a theorem has been proven. It is proven using definitions and postulates. So our first theorem is the perpendicular bisector theorem. What do you suppose is happening in here? I bet we've got some perpendicular lines, and I bet there's some bisecting going on. So perpendicular means right angle, bisector means 2 congruent. So let's look at our theorem. Our requirement, if a point is on the perpendicular bisector of our segment, then, this is the result, it is equidistant from the endpoints of that segment. So let's go take a look here. We have a point, that's point P. Point P is on the perpendicular bisector. How do we know this? Perpendicular, bisect. We can be shown on a diagram, we can be told. Line PM is perpendicular to segment AB, and the length of MA is the same as the length of MB. That means that the segments are congruent. So we have a point on the perpendicular bisector, either shown on the diagram or written out in words. Then what happens? Then our point is equidistant from the endpoints of the segment. Here is the endpoints of segment AB, the segment that it's perpendicular to. It is equidistant from those points. So we can mark these two congruent. So if these two segments are congruent, then we can say their lengths are equal. If you are on a perpendicular bisector, then you are equidistant from the endpoints of the segment. Now it doesn't matter where this point is. If we put a point down here, it would be equidistant. If we put a point up here, it would be equidistant. If we put a point down here, it would be equidistant. Okay, good stuff there. Next is the converse of the perpendicular bisector theorem. The converse. Converse means that we switch our if-then statements. So our result becomes our requirement becomes our result. So let's look at this. What was our result up here? Equidistant from endpoints. So we start out with if our point is equidistant from the endpoints of the segment. What was our requirement up here? The point is on the perpendicular bisector. So our result this time is then the point is on the perpendicular bisector of the segment. So let's look at our diagram here. We are given a point and it is equidistant from the endpoints of our segment. And we are shown on the diagram by congruent marks or told in our given length PA equals length PB. That means that they are congruent. They are equal lengths, equidistant. If that is true, then our result is that our point is on the perpendicular bisector. So here is our point P, and we know that it is on this line that is both perpendicular to this segment and bisects the segment. So we can say that line PM is perpendicular to segment AB and that length MA is equal to length MB because these two segments are congruent, bisect, right? Congruent parts. Definition of congruence is equal length. So these are some really special theorems here, and they follow what we have learned about angle bisectors, and we'll be learning about perpendicular bisectors. We are going to construct the perpendicular bisector of a segment, and this is one of the easiest ones. Looking at this segment here, you should be thinking of Euclid and his triangles again and his circles that make those equilateral triangles. We are going to use our compass, and the key here is we can use any length. It simply has to be greater than half of our segment because our circles need to intersect. But let's give it a shot at using it as the length of our segment. So I'm going to draw my first circle, and then I am going to move it over to the other point, keeping the same length, same compass setting. Draw my other circle, and then what do I end up with? I end up with 2 intersection points that will let me connect, and I now have a perpendicular bisector. It is perpendicular and it bisects my segment. Now let's do a quick what if we chose a smaller setting? And I am just going to do this part of the circle, and then I'm going to move my compass, and I'm going to do this part of the circle, and check that out. I get the same intersection points. So you can draw the entire circle or just the parts that you need. You can use any radius you want for those circles. We have the same idea happening on all of them. Perpendicular bisectors are fun.